This video will cover the first part of section 6.3, which is looking at separable differential equations. In the first video in 6.2, we did an introduction to separable differential equations, and today we're going to look at those equations a little bit more in depth. And in addition to looking at just basic solving separable differential equations, we're actually going to be looking in these notes at 3 different past AP problems dealing with this topic. So we're going to go back and do a little bit of review with just our basic calculus as well. So what I want you to do is I want you to actually pause the video for a second, and I want you to try A and B on your own, and if you need help, unpause it. I'll kind of do each part separately, and then we'll pick back up and I'll kind of go through C more in depth. Okay, so pause the video and do A and B on your own. Okay, so the first one is very simple. Just find the slope. They give you the slope here. They give you the point here, so that's just a matter of plugging in for x and y and solving. So the slope at the point x equals 1, the slope is 1/2. So for part B, they're asking you to write the equation for the tangent line. Again, it's very easy given the slope from part A and the point. And then we have to use that to approximate f of 1.2. So going back, we don't know what the function looks like. We know this is the slope, so this is f prime. And we're trying to figure out what f looks like. And so what they're using is, given that slope, and finding the tangent line. So we could have f looking like that, all right? And so we don't know what f is, but we know the slope. We know at the point 1, 4, let's say that is right here, okay? So let's say that's 1 and that's 4. What they're asking is, we only know that 1 point. We don't know how the rest of it looks. That's just an estimate of what f might look like. So what they're saying is, if I draw the tangent line of f, let's just pretend it looks like that, at that point, now what would 1.2 be? So that point right there, what would that be on the line? Okay, so that's what you're doing. You're just estimating a value for that. Okay, so now for part C, what they're doing is we're actually going to try to find an equation for f by solving the separable differential equation. So this is like what we did in the first video, but just a little bit more in depth. So you can see that we want to separate these values by basically cross multiplying here. This is a very basic one. So 2y dy is equal to 3x squared plus 1 dx. And at this point now, we can take the integral of both sides. Integral of 2y is going to be y squared. Again, you don't have to put the plus c on this side. And then the integral of 3x squared is x cubed plus x and then plus c. All right, so we want to find f of x here. So we're going to go ahead and we can take the square root here, but we want to use the initial condition 1, 4. So that means we're not going to leave it in terms of the c value. We're going to actually calculate the c value. I'm going to go ahead and do it at this point, and then solve for y finally in the end. So I'm going to plug in 4 for my y, and 1 for my x to figure out what that plus c value is. So that's c. When you solve, 16 minus 2 is 14. And so now, if I plug that 14 back in and took the square root, you would get x cubed plus x plus 14. Also, again, note that I did not put plus or minus, because since when you plug in 1, you get a positive value of 4, the square root is going to be positive. So our f, the estimated conjecture up at the top, obviously that's not what f is going to look like, but this is what f is actually going to look like with the square root function. Okay? So now we estimated in part C, using the tangent line, what f of 1.2 would be. And we found 4.1. So now what we're going to do, now that we actually know the function of f, we're going to use that to calculate what f of 1.2 actually is. We need to set a f of x. Okay. All right, so let's calculate f at 1.2. Go ahead and do that on your own. So as you can see, I got 4.114. 4, which is very close to 4.1, but a lot more accurate. And again, make sure to do 3 decimal places if necessary. Okay, so that's pretty basic AP problem with separable. So let's try another one that actually combines what we did in the last video with growth and decay and the differential equation. Okay, so we have more of an application type problem. We have the rate of consumption of cola in the United States is given by this formula. And what you notice about that formula, that is that exponential growth and decay, where S is measured in billions of gallons of cola per year consumed, and T is measured in years from the beginning of 1980. All right, so we want to use this model, and in order to use it though, we have to find those constants, C and K. So for part A, it says the consumption rate doubles every 5 years, and the consumption rate at the beginning of 1980 was 6 billion gallons per year. Find C and K. Well, C is very easy. Remember, C is like what your initial value is. So C, and I don't know what's going on with my pen. Hold on. I think I'm writing too fast. Okay, so C would be that 6 billion. And since we're already measured in billions of gallons, C is just going to be 6. So what I want you to do now is use the knowledge that we did from the last section to find the K. Okay, so using the knowledge that the consumption rate doubles every 5 years, if we started out with 6, doubling would be 12. So there's my equation, and then I solve for K. This is a calculator question, so I'm going to go ahead and solve for K using the calculator, and you would get 0.139. Now, you will be using that K later on, so make sure you can either use the exact value, natural log of 2/5, when you calculate later, or you would have to use the whole thing, go up and copy in your calculator the 0.139. You cannot just use 0.139. You have to use all decimal places so that your following answers, the other parts, are going to be as accurate as possible. All right, so let's look at part B. It says, find the average rate of consumption of cola over the 10-year period beginning January 1st, 1983, indicate units. All right, so go back to what we were given. We were given the formula for the rate of consumption of cola. And now we're finding the average rate of consumption of cola. So we're finding the average, that whole thing, is S of T. So we're finding the average of S of T. That, in other words, is the average value of S of T. And hopefully when I said that clued you in that we're doing the 1/b minus A thing, times the integral from A to B. Now, if we're starting in 1983 and T of 0 is 1980, all right, then that's going to be starting at year 3, and over the 10-year period, that would be ending at year 13 in 1993. So we're going to say that's 1/year 13 minus year 3, add up from 3 to 13 of S of T. You don't have to, on the AP test, rewrite the actual formula for S here. But it would actually be kind of a good idea because we never did that. This is definitely going to be a calculator question, so you would not be expected to integrate this. But let's go ahead and find what S of T would be. So we know that at the beginning we have 6E, and then our K value was the 0.139T. And again, when you put that in the calculator, do not just put in 0.139. You could put in natural log of 2/5 or go back and copy from the previous line. So if you haven't already gotten out your calculators, if you'll go ahead and do that, I'd like to make sure that we are good with putting this integral into the calculator. Okay, so just a reminder, for integral, you can press this button here and get the format for your integral. There we go. Okay, so then we're going to go from 3 to 13. Sorry guys, this is actually my first time using this on the computer. So now we're going to plug in our equation. Okay, so I just paused it so that I wouldn't waste a whole lot of time. All right, so hopefully that's what you got. So again, as you see, I didn't have that value for natural log of 2/5 sitting in my calculator, so I retyped natural log of 2/5 to get the most accurate answer. And this is not my answer yet because this is just the integral. Now I have to divide by 10 in order to get the average rate of consumption. But I want to talk about that 196 number for a second, because what I've done is I've accumulated from 1983 to 1993 the amount of COLA that has been consumed. So that actually, that 196 represents the total amount of COLA that was consumed in the U.S. in those 10 years. So just making sure you understand what that number represents. All right, but we don't want that. We want to find the average over those 10 years, so divide by 10, and we get 19.681 billions of gallons was the average number consumed per year. Okay, so let's just put that here. So we have 19.681, and so that probably gives you 1, maybe 2 points there. And then let's go ahead and indicate the units to get all the points, and that would be in billions of gallons. And it's an average rate of consumption, so we have to have per year. Okay? All right, so moving along, we're going to look at part C, trapezoid rule. So like I said, these are going to be some good review questions involved in here. So trapezoid rule, we're going to use that to estimate the integral from 5 to 7 of t. So just like we just did, we found, back in our calculator, we found the integral from 3 to 13, and I told you that 196 number here was the total amount of COLA consumed in those 10 years. So that's essentially what we're finding in part C, but from 1985 to 1987, and we're not using our calculator, just plug it in, we're actually having to use a trapezoid rule. All right, so what you need to find is, it says, I want trapezoid was 4 equal subdivisions. So we're going to start with the year, so I'm going to make a little chart over here, and we're going to start with the year 1985, and then if we want 4 equal subdivisions to 7, we're going to have to go up by halves. So I want to know at 5.5, at 6, and then at 6.5. And so you see you've got your 4 subdivisions here. Okay? All right, so you need to calculate what the rate of consumption of COLA was for each of those values. So go ahead, let's do that in the calculator. Now, I'll show you how I would do this in the calculator. You might have a different method, and that's totally fine. So I would go ahead and plug in my equation into the calculator. And then I would use the such that button, which is the control equals. So I would use that such that button there, and then say x equals 5. Okay, so that's 12. Then if you just go back up, hit enter, and now I want to know when x equals 5.5, and then continue doing that for each number. Okay, and make sure that you are doing this on your calculator instead of just watching me, because it's important that you practice those strokes to get used to it. Okay, so I'm going to go ahead and find the other 2, and then we'll talk about what to do with those. Okay, so I found all those values. They're sitting on my calculator, but I want to talk about how you could even get, without calculating all those points, you could get at least 1 point here, even without even doing any math. So the way that I would set this up is I want to estimate this value, so I'm going to rewrite integral from 5 to 7 of s of t dt, and I'm going to say that is approximately equal to. Now, trapezoid rule, remember the area of a trapezoid is 1/2 times, in this case, uniform width, and then times base 1 plus base 2. So we have in common the uniform, or the 1/2, and then the uniform width here is also another half. We'll mark that as 0.5, so you can see that width there of 0.5. You can only do that if you have a uniform width. All right, so then we have base 1 plus base 2. So remember that with each of these trapezoids, they have the middle base in common. So the very first base at 5 is only going to be counted once. So that's going to be s of 5 plus, and then 2 times s of 5.5, 6, 6.5, and then plus s of 7 is the endpoint, 7 only gets counted twice. Sorry. If you wrote just that down right there, you would probably get 1, maybe even 2 points. And then the final answer is worth a point. So you actually don't have to write down each of those values that we found in the calculator. Now, that's just up to your choice, because you have to write down all the s of 5, s of 5.5. But at this point now, I don't have to write down each of those values. So what I'm going to do is I'm going to plug all this into the calculator, So go back to your calculator, and hopefully you have sitting up here all the answers for each of those S values. So I'm going to pause, and I'm going to plug in my formula. Okay, so before I hit enter, I want you to see what I did here. So I have 0.5 for the trapezoid rule, 0.5 for the uniform rule, or uniform width, and then inside parentheses I have my first value as a 5 plus 2, and then parentheses inside of there I've got my next 3 values. And then make sure you close parentheses and add the final value. Okay, so I just wanted to show you my form there, and now we get 27.668. Okay, so that's my final answer. 27.668. Notice we did not have that they wanted you to include units here, because looking at Part D, that's where they want you to explain the meaning of what you just found. So Part D is really like the units and explanation of that 27.688. We've already talked about it with the first example, that this is representative of the total consumption of cola from year 5 to 7. But you have to be very, very specific. So I'm going to write down what the meaning is, how specific you have to get in detail, and so you can copy it once I unpause. Okay, so as you can see, I've made this extremely detailed. I have to say from the beginning of 1985 to the beginning of 1987, because that's how it was phrased in the problem. If you just said from 1985 to 1987, at what point are you talking about? In the middle of the year, from the beginning of 1985 to the end of 1987? You have to be very specific. The total consumption of cola in the U.S., that's how they phrase the problem, so I've got to repeat the problem, was approximately 27.688 billions of gallons. So I'm not quite sure how much this would be worth, probably 2 points. So yeah, you just have to be very, very specific. Like I've said in the past, regurgitate the problem. All right, so we have one final question to do, and it also is going to be a calculator question. Okay, so now we have a skydiver, and we have her velocity in feet per second, and after her parachute opens, her velocity satisfies the differential equation. So what that means is this is her rate of change of her velocity. And remember, this is after her parachute opens. With the initial condition that her velocity at the time that the parachute opens was negative 50 feet per second. So what I want you to do is, now it's your turn to try to do the separation of variables by yourself. So I want you to do part A by yourself to see if you can find an equation for V, given, make sure the initial condition at 0 is negative 50. So go ahead and pause and do that yourself. Okay, so I want to mention this here. What I did is, you could have just divided by negative 2V minus 32, but I like to take out the constants. So I actually factored out a negative 2 first, so that all I would be divided by is V plus 16. Because this integral over here with on the left side, it's going to be more complicated since it's in a denominator. So I like to make this as simple as possible. So anytime that you can factor out a value, that would be helpful. But you could have still done it if you had divided by the whole thing at the very beginning. Okay, so once you isolate V, then you can plug in to find your C. So plug in the initial condition to find C value, and then here is my final answer for V. There are other ways of doing it, but this is what I find to be the simplest for me. Okay, so now our last 2 questions is pretty simple. It says that terminal velocity is defined as the limit as t approaches infinity of your velocity function. So we want to find the terminal velocity of the skydiver to the nearest foot per second. So that means that we're going to find the limit as t approaches infinity of this velocity function that we found in part A. Okay, so what happens is, as t approaches infinity, this e to the negative 2t is going to approach e to the negative infinity, which that approaches 0. So then the negative 34 cancels out, leaving you with negative 16 feet per second. Okay. And then for part C, it says that it is safe to land when her speed is 20 feet per second. And notice here that we now change to the word speed. At what time t does she reach this speed? So we're given velocity, and speed is the absolute value of velocity. So we want to set my velocity equal to not 20, but negative 20. So we're going to put negative 34 equals negative 20 there and go ahead and solve. So if you will, go ahead and solve that on your own, and we'll see if we get the same answer. Alright, so this is just the basic problem that we have been solving using natural log. So our final time is 1.070 seconds is when she reaches that velocity after her parachute opens. Okay?